In this video, I will be explaining you an important theorem that you can see in the third unit of measure and integration, that is Beppo-Levi's lemma. Is that right? Beppo-Levi's lemma. You can see the statement here. It's a named lemma, no? So in this examination, they don't ask you with a statement. Okay, they will ask you just like this. State and prove Beppo-Levi's lemma. Okay, so we have to write the statement now. So let's learn the statement using my notes. Here you can see the statement from this to this. You are having statement of this Beppo-Levi's lemma. Okay, so first you have to consider this function fn. Okay, so let fn be an increasing non-negative measurable function on E. Is that clear? So here fn means what? Here you are having f1, f2, f3 till fn. Okay, so this function is increasing. It means f1 less than or equal to f2 less than or equal to f3. Increasing, no? Yes. So this is let fn be an increasing, and it's non-negative. It's not a negative function. Okay, non-negative and measurable functions on the measurable set E, and integral fn over E. That is when you find the integration for this, that is bounded. Integral fn over E is bounded. Then if these two conditions are there, then sequence fn converges to f point-wise on E, that is finite almost everywhere on E. What is that? Sequence. This is sequence. Okay, sequence fn converges to f. This f is a measurable function, converges to f point-wise on E, that is to a measurable function f on E to a measurable function f, that is finite almost everywhere on E. That is, they are talking about this fn converges to f point-wise on E, and this function f is finite almost everywhere on E. Okay, that is what the meaning. Is that clear? Let me tell you. First you have to take a sequence of measurable function, that is fn. This is an increasing non-negative function, and then you are taking integration to this fn, that is bounded. Then what you have to prove is fn, sequence fn converges to f point-wise on E. This f is a measurable function, that is this f is finite almost everywhere on E, and this condition is also there. This is what we have to prove. Okay. Okay, let's learn the proof of this lemma. It's very easy. Okay, this much only you are having the proof. So first what you have to do is you are defining f of x equal to limit n tends to infinitive fn. Okay, so you are defining this. Now you are using a result that you will get from monotone convergence theorem. So by monotone convergence theorem, you are writing this integral f over E is equal to limit n tends to infinitive integral fn over E. Now the statement we are having, this is bounded, no? So you are writing that. Therefore, if this is bounded, its limit is finite. This is bounded, therefore you can say its limit is finite. Now you are using a proposition. By a proposition, f is finite almost everywhere on E. If fn having limit and that limit is finite, then you can use a proposition and write the sentence f is finite almost everywhere on E. If that's so, then this can be written like this. Limit n tends to infinitive integral f1 over E is equal to limit is equal to integral f over e, and this value will be finite. Less than infinity means what? Finite. Okay. Okay, is that clear?